You open a map app and ask for the fastest route. You send a friend request and it tells you how many mutual connections you share. You drop a piece in a flood-fill puzzle and watch color spread outward in perfect concentric rings. All of these are the same algorithm working under the hood. It is called breadth-first search, and in the next 10 minutes you will understand exactly what it is doing, why the queue is the critical piece, and why the algorithm is mathematically guaranteed to find the shortest path in an unweighted graph. Let us start with the core question. You have a graph. A graph is a set of nodes connected by edges. You want to find the shortest path from one node to another. Why does breadth-first search guarantee that you find it, and why does no shorter path to the target exist? The answer comes down to three properties. First, BFS explores nodes level by level. It visits every node at distance 1 before it visits any node at distance 2, and every node at distance 2 before any at distance 3. Second, the order of exploration is controlled entirely by a queue, which is a first-in, first-out data structure. Swap the queue for a stack and the level-by-level property immediately breaks. Third, BFS only works for unweighted graphs where every edge costs exactly one hop. If your edges have different weights, you need Dijkstra instead. BFS runs in O of V plus E time, where V is nodes and E is edges. It uses O of V space for the queue and the visited set. These are the guarantees. Now let us see how each part delivers them. Before BFS can run, the graph needs to exist in memory. The standard representation is an adjacency list. Each node maps to a list of its direct neighbors. For a graph with 7 nodes, A at the root, B and C at level 1, and D, E, F, and G at level 2, the adjacency list for A contains B and C, the adjacency list for B contains a D, and E. This structure uses O of V plus E space, proportional to the number of edges rather than V squared. That distinction matters because real-world graphs like road networks and social graphs are sparse. Most nodes connect to only a handful of others rather than to every node in the graph. A full adjacency matrix would waste enormous memory on those empty cells. The adjacency list does not. It is also cache-friendly during traversal because each node reads only its own compact neighbor slice, not an entire row of V entries. For the 7-node example graph, the total storage is 7 nodes plus 12 directed edge slots, roughly 19 units rather than 49. Now the queue. The queue is the engine of BFS, and it is what separates BFS from depth-first search at the most fundamental level. A queue is first in, first out. The first item you push in is the first item you pull out. A stack is last in, first out. That single structural difference determines the entire character of the traversal. When you enqueue a neighbor, it goes to the back of the queue. When you process the next node, you pull from the front. This means nodes discovered earlier are always processed before nodes discovered later. Because nodes discovered earlier are always closer to the source, the algorithm naturally processes closer nodes before farther ones. Swap the queue for a stack and you get depth-first search. DFS plunges as far as possible along one branch before it backtracks. It does not guarantee shortest paths in unweighted graphs. BFS does, and the queue is exactly the reason why. This is worth pausing on. The queue is not an implementation detail, it is the invariant. Without it, the shortest path guarantee evaporates and you are left with an algorithm that finds a path but cannot promise anything about its length. Let us walk through a traversal step by step on the 7-node graph. Step 1, enqueue the root node A. The queue contains A. The visited set is empty. Step 2, dequeue A. Inspect its neighbors B and C. Neither is visited. Mark both visited and enqueue them. Queue is now B. C visited contains A. Step 3, dequeue B. Its neighbors are D and E. A is already visited. Mark D and E visited and enqueue them. Queue is now C. D. E. Step 4, dequeue C. Its neighbors are A, F, and G. Mark F and G visited and enqueue them. Queue is now D, E, F, G. Step 5, dequeue D, then E, then F, then G in order. None have unvisited neighbors in this graph. The queue empties and traversal is complete. Every node was visited exactly once. Every edge was inspected at most twice, once from each endpoint. The total work is O of V plus E as promised. Now for the proof that BFS finds shortest paths. The proof is by induction. Base case, the source is at distance 0 and is discovered immediately when we initialize the queue. Inductive step, assume every node at distance D was discovered correctly. When we dequeue a node U at distance D, we inspect all of its neighbors. Any neighbor V not yet visited must be at distance D plus 1 because the shortest path to U is D hops, and the edge from U to V costs 1 more hop. We mark V visited and record its parent as U because V was not already visited. No shorter path to V has been found. The distance we assign is correct. The induction holds across all D. BFS is provably optimal for unweighted shortest paths. To reconstruct the actual path, you maintain a parent map as BFS runs. When you discover V through U, record parent of V equals U. To recover the path from source to target, walk the parent pointers backward from target to source and reverse the list. Here is the complete Python implementation. You import dec from the collections module because dec gives you pop left in O of 1 time. Regular Python list also supports removing from index 0, but that operation shifts every remaining element and costs O of n. which would change BFS overall complexity from O of V plus E to O of V times E. The function accepts the graph as an adjacency dictionary and a start node. You create an empty visited set and initialize the deck with just the start node. You immediately add the start node to visited. Critical detail is that you mark a node visited at the moment you enqueue it, not at the moment you dequeue it. If you wait until dequeue time, the same node can be enqueued multiple times before it is ever processed, wasting memory and causing redundant work on graphs with many cycles. The main loop runs while the queue is not empty. You call popleft to retrieve the next node, then iterate over its neighbors. For each unvisited neighbor, you add it to visited and append it to the queue. 12 lines. Completely transparent once you understand how the queue enforces level order. Breadth-first search appears across the entire software industry. Social networks use BFS to compute degrees of separation. LinkedIn runs a variant of BFS when it tells you a person is a second-degree connection. Web crawlers use BFS from seed URLs, treating pages as nodes and links as directed edges, exploring the web level by level where each level is one additional click from the seed. Puzzle and game AI solvers use BFS to find minimum move solutions. 15 puzzle, Rubik's Cube partial solvers, and maze generators all model the problem as a graph and apply BFS to guarantee fewest steps. Networking protocols use BFS for spanning tree construction and minimum hop routing between routers. The spanning tree protocol that prevents switching loops in Ethernet networks is a direct application. Every time a switch boots and discovers its neighbors, it is running a constrained BFS to elect a root bridge and build a loop-free topology. Beyond the basic algorithm, there are 3 important variants worth knowing. Bidirectional BFS runs 2 simultaneous searches, one forward from source and one backward from target, stopping when the 2 frontiers meet in the middle. If naive BFS explores B to the power of D nodes, bidirectional BFS explores roughly 2 times B to the power of D over 2, a dramatic reduction on large graphs. Multi-source BFS enqueues multiple starting nodes at time 0 and propagates outward from all of them simultaneously. This is equivalent to adding a virtual supersource connected to all real sources with zero-cost edges. Solves problems like distance to the nearest facility on a road graph or the rotten oranges puzzle. 0 and BFS handles graphs where edges cost either 0 or 1. You use a deck, pushing 0-cost neighbors to the front and 1-cost neighbors to the back. This achieves O of V plus E time, faster than Dijkstra for this specific edge-weight structure. The complete picture of BFS is 6 components working in concert. An adjacency list stores the graph in O of V plus E space. A visited hash set provides O of 1 membership checks. A deck gives O of 1 enqueue and dequeue operations. The BFS loop touches each node once and each edge at most twice. A parent map records how each node was discovered so any path can be reconstructed in linear time. The result is the minimum hop path from the source to every reachable node. Time complexity O of V plus E space complexity O of V provably optimal for unweighted shortest paths, simple enough to implement correctly in a dozen lines, running in production systems around the world every single day. That is breadth-first search. Thanks for watching.